Right. Final topic for today is loops and iterations. Oops. Okay. We will look at one of the very popular loops, which is a for loop. Okay, because I rarely use while loops. So let's focus on the for loop. For example, let's assume a use case. For example, you have a list of numbers. You want to pick one number at a time and you want to print the square of that number. How can you do that in Python? So first create a list of numbers. The question one, please focus. OK, question number 1, 3.1. Let's call it 3.1. Create a list of numbers and print square of them, square of each. OK, let me give you a shortcut on how to create a long list of numbers. OK, my numbers. There is something called a range function in Python. You can start at a particular number, end at a particular number. That ending portion is not included. OK, one number before it is included. So basically it will be a list from 0 to 100. It is a pseudo list. So in order to convert it to a list, you have to provide the list command here. OK, so you can see if I print the my numbers, it is from 0 to 100. Now for number in my numbers, print, let's first print one by one the number. OK, number. So you can see it is picking up one number at a time. So for number in my numbers, so it will pick one element at a time. So number becomes at the first step of the iteration, number becomes 0, 0 is printed. Then it goes again, 1 is picked up, 1 is printed. So basically it picks up. So this statement number in numbers, for number in numbers, it's as if you are picking up one by one every number, then running the code cell within the for loop. OK, so right now we are printing the number as it is. So we don't have to worry about it. Also note that no one likes this tall giraffe. We can provide a separator here to be space. What happened? /t. Nope, still not working. Why is it not working? Just let me check. Oh, end, sorry. End should be space. So you can see 0 is picked up, 1 is picked up, every number is printed because the current execution of the for loop involves just printing the number. But what if now I square it? So you can see 0 is picked up, the square of 0 is printed, 1 is picked up, square of 1 is printed, 4 is picked up, 2 is picked up, square of 2 is printed, and so on. What if I wanted to add 10 to the square of the number and then print it? You can see accordingly the calculations are modified. What if I wanted to subtract 10 from this 10? You can see again the same thing. What if I wanted to add the number cube to this? So you can do whatever you want within the for loop, but just that it will be repeated on every number in that list. So this part of the code is always a list or a tuple or an iterator. It should have a ordered arrangement of elements. For example, for letter in Divyanshu, because this is also an ordered arrangement of something, right? Print letter and should be a underscore. So you can see every letter is picked up one by one and printed one after the other. If you ignore this end, you can see every letter is picked up one by one and it is just printed. OK, so this is a slight introduction about easy little introduction about what is the logic of a for loop. Now let's solve some problems. Okay, so we have this my numbers list, right? And we have also seen how to square it. What if we wanted to create a my squared numbers list, which is initially an empty list? Okay, what we will do is we will take the my numbers list, take one by one element from that, square it, and keep on adding that number to this list, right? So we know how to do that, right? So for number in, let's use n, okay? For n in my numbers, n squared is equals to n to the power 2, okay? My squared numbers equals to my squared numbers plus, because we know that two lists can be added together. So now if I look at my squared numbers, it is a list with the square of all the numbers which were stored in my numbers. A very simple application of a for loop. Okay, good. Now everyone knows something about the Newton-Raphson's method. A sweet application of a for loop to solve some actual problems. Okay, and if you understand this, this can help you solve a lot of problems in whatever numerical textbooks you are reading. I'm from the reservoir engineering background, so I can see that I solved a few examples in reservoir engineering books like Tariq Ahmed and LP Dake. I mean, if you are reading some other book or whatever domain you belong to, there'll always be cases which will be solved using numerical methods, because the root finding of complex equations, which are called transcendental equations, they are not possible using analytical methods. Rather, you need to use numerical methods to solve them. And Newton-Raphson's method is just one method which helps you do that. It helps you solve a particular equation, and it always converges in terms of the solution. So the solution will almost always be there. You can almost always find out the solution. Okay. So let's look at a few Newton-Raphson's example solutions. Okay. And then we will conclude our session. Okay. So the basic formula for Newton-Raphson is x new equals to x old minus fx divided by f dash x. Okay, so this is the, and you keep on repeating this. So basically you have an fx equals to 0 kind of thing. You have an fx equals to 0 kind of thing. You have fx equals to 0 kind of thing. This is on the left hand side. You have the entire expression that you want to solve for. You take the initial root x, initial guess, whatever alpha, whatever value you want to take, and you keep on updating that using the Newton-Raphson's concept, which is this one. Where this comes from the Taylor series expansion of any function up to the first order. Okay, so we can solve a few things, but the idea here is the repeat part that you see here. The repeat that you see here, this repeat is basically what for loop will help us to do. Repetitive task is what for loop helps us to do. Okay. First, let's see how to find a square root of a number using a Newton-Raphson's method. Square root of a number. Okay, basically the equation here is x squared equals to n. Okay. So basically we want to find x here. Okay. So what is fx? Fx is, let's create a function. Def fx takes in x, returns what? takes two things, f, x, and n. Basically, what will be the f dash x? So in this case, fx is equals to what? It is equals to, take everything to the left hand side, x to the power 2 minus n equals to 0. So basically x to the power 2 minus n becomes your fx. Okay. And what is f dash x? F dash x, it is what? 2x. As simple as that. 2x. Okay. So fx will be what? X to the power 2 minus n. And what is f dash x? It is 2 multiplied by x. Okay. Now, how many types? What will be the initial guess? Let's start with initial guess. Okay. X initial guess equals to, and let's also take n. N is the number we want to find the square root of. Let's say n is 100. X initial, let's take it to be 0, or let's say 2. Okay. What is Newton-Raphson's method? Newton-Raphson's method is x new is equals to x old minus fx divided by f dash x. So basically, let's not use the name x initial. Yeah, let's use only x underscore, and we will repeat it for repeat in how many times you want to repeat? The range of, let's say 1,000 times you want to repeat. What thing you want to repeat? You want to update the value of x underscore. X underscore equals to x underscore minus fx upon fx. What is fx? You pass on x underscore and you pass on n divided by f dash x. What is f dash x requiring? It only requires us to provide x underscore. You repeat this for 1,000 iterations. You can see your initial guess. You did not know the square root of 100. You assume that it was 2. But after you solve it for 100 iterations or 1,000 iterations, you can see the underscore x underscore's final value is 10.0. Okay. For example, let's use 26. Let's use a number. Okay. Let's use a very complex number. 25689632112. Okay. 15.52. And we take the same initial guess. And this is a proof that Newton-Raphson's method almost always converges. Okay. So now if we repeat it, let's verify now. This is the Newton-Raphson prediction of square root of x, square root of n. Okay. This is the Newton-Raphson prediction. Let's try by n to the power 0.5. You can see how close both of them are, almost exactly equal. There might be some differences in later significant digits, but they are almost exactly equal. If you reduce the number of iterations, let's see how close we get in 10 iterations. You can see in 10 iterations, you are not close. Okay. But if you increase it to, let's say 20 iterations, if you increase it to, let's say 20 iterations, you can see now again. So it requires somewhere around 10 to 20 iterations to get from 2 to 15, 2 to the actual root. Okay. So basically, this was all about this thing. I will share a link with you guys in the chat so that you take this solving the Newton-Raphson's algorithm, that example, and you see how reservoir engineers can use Newton-Raphson's method to find liquid permeability in core analysis. Okay, so I'll be sharing this in the chat. Let me open the chat. This is from my GitHub repository. The reference textbook for this is Tariq Ahmed, which is a reservoir engineering book. A very important problem is that if you bring in core samples from the actual rock and you test for permeability in laboratories, there'll be a difference. If you are using air for permeability checking, air has a benefit that air can, jump from the solid particles. Air does not stick to the solid particles because air is normally non-wetting. So the permeability that you find using air as the fluid will always be higher. But there was a scientist called Klinkenberg, and what they did was they provided a complex looking equation that can be used iteratively to start with air permeability as the initial guess, and you can iteratively use that equation and the final solution will converge to the liquid permeability. Okay, so this entire concept that we just learned in Python, back when that Klinkenberg effect was created, they did not have computational resources, so they used to do that by hand. Now you can use the same logic. All you have to do is replace the fx and f dash x accordingly, and the same logic for the number of iterations can be used to find out liquid permeability using air permeability. And you will see that the Newton-Raphson method actually gets you very close to the actual, observed liquid permeability. Okay, so just imagine pure mathematics and computational resource helping you find out the reality of some physics. Okay, you had no clue about what was the actual liquid permeability. All you did was you used Newton-Raphson's method to iterate from the initial guess to reach to the ultimate liquid permeability. So this is, I mean, before we meet tomorrow, I would like you guys to have a look at it. I've shared it in the chat. Now I think we can have a few minutes for questions and answers. What is math.exp? Yeah, thanks for reminding me that. So one thing that I want you guys to know is, so let me find that squarer function. Where was that? Squarer. So there's something called a module in Python. Okay. So if I go to this folder, I can create a Python script. Okay. My funcs.py. And you don't have to do this. This is just to explain some concept. Okay. So I have copied that function that I created in this script, and I can create one more function similar to this, cuber. Okay, cuber, and I can return x to the power 3 x cubed x cubed. Okay, now this is called a module because it is a collection of functions within a script. .py is a symbol for a script, Python script. Okay, now it is just a repository of various functions that you have created. Now I can use this. This is the benefit of creating functions, because now what I can do is I can import my functions. What was the name? My funcs. Okay, and I can use whatever functions were there in my funcs. My funcs dot squarer new 3. It returns 9. Now math is one similar thing, similar to a my funcs, and it has a similar function like the squarer new, which is exp and a lot of other mathematical functions. Okay, so basically this is what I did when I did math.exp. What I did there was I imported math first, imported math, import math, and then math.exp. to the power 3. It's similar to, it's similar to 2.71 to the power 3. Sorry, to the power 3. Okay, this is highly approximated, but this gives you the actual value. So do you understand what this is? It's just here we access the squarer function from a particular module. Similarly, here we access the exponential function from this particular module. Am I clear? Hope I am. Any other questions? The plot from session 1. Okay. Plot, we will have a separate session on plottings, so that's not an issue, but yeah, here it is. Dot plot. Porosity is reducing with depth. Right now, this is not even a correct plot because the depth axis has to be changed. So this is just a slide demo. Anyone, any other doubts? Feel free to ask before we wrap for today. These three things are very important: the for loops, the functions, and the if else's, because this is where programming actually starts. You will keep on applying logics and converting them to these kind of programs every now and then. You will create functions a lot. I mean, in data science, you import data, you can create a function that has a few data processing steps. For example, if you have a data set which has some problems every time, it's coming out of a software. For example, it is coming out of some production profiling software, which has yeah, I will upload the codes after this session to the Teams folder itself. You can access it from there. Okay, and also I've shared the link to my GitHub repository in the chat. I have a huge set of codes and everything, all my learning journey up there on the GitHub repository. There are Python courses there, there are machine learning courses, data science courses. So if you have the appetite to learn more on your free time, feel free to hop over there, connect with me on LinkedIn for more resources, whatever you want to do. So yeah, we can create our functions, and every step of the data science workflow can be a different functions, so that further in the future you can reuse that same function for some other project as well. And that's the benefit. Similarly, for example, the squaring and cubing, this is a fundamental math kind of thing. This is just an example. I can use the math squarer and cuber across my projects. Similarly, as a reservoir engineer, I know fractional flow theory is useful across the projects. I can use them for simulations or whatever. So why not create a separate module and have all the functions stored there? And that's why functions are like they're priceless. So please focus on these functions today after the session, and we will be starting with data analysis tools tomorrow, and practice a few projects by the evening tomorrow. All right, I think we are good to wrap things up for today. Anyone, if you have any doubts, otherwise, if not, I think we're good to go. Looks like there are no doubts. I think, okay. Thanks, everyone. Happy Saturday. Happy Sunday. See you tomorrow.
Thank you, Divyanshu, and thank you all for joining. Let's meet tomorrow at 1:30 p.m. Thank you.